Okay, so I think it's worth pausing for just a minute before we talk about the next thing and think about what we know so far. So we know something about what a linear system is, and we know how to represent a linear system with an augmented matrix. And we know how to perform these elementary row operations that transform the matrix without changing the solutions to the linear system that the matrix represents. Okay, so why are we wanting to do all of these things? Well, if we want to solve a linear system, it turns out that there's a very nice algorithm for doing that that can be easily implemented in computation with a computer. And the goal that we're going to aim for when we're performing these operations is to get an augmented matrix that might look like this turned into something that looks more like this. And if we can do that, then we've transformed a really messy looking linear system. Like, think about writing out these equations, right? This is 3x1 plus 7x2 plus 6x3 plus 2x4 equals 7, and so on. This is something that looks like it's going to be pretty hard to solve just using these techniques of substitution. This, however, this is going to be easy to solve. So write down these equations from the augmented matrix, and we see that x1 is equal to A, x2 is equal to B, x3 is equal to C, and x4 is equal to D. Those are exactly the equations that are represented by this augmented matrix, and that is the solution that we would be looking for, right? So we just found the coordinates of the point of intersection of four hyperplanes in a four-dimensional space, right? Because it's a 4D, a four-variable system. That's the dimension of space that we're living in. Okay, so how do we get from here, this messy one, to something that looks a little bit cleaner like that? Well, the way that we do it is by performing in succession elementary row operations to take a matrix from its original state into something that's called echelon form, or even better, reduced echelon form. So let's look at what that is. Let's start with just echelon form. So we say a matrix is in echelon form if it satisfies two conditions. The first one says that any rows of all zeros have to be at the bottom. The second rule says that the leading entry in any row has to be to the right of the leading entry in any row above it. Okay, and just to make sure we're all on the same page, I'll just say that the leading entry is the first non-zero entry in a row. So let's take a look at an example. Okay, so this matrix is in echelon form. It's an augmented matrix for a linear system, but we don't necessarily have to be talking about linear systems. We could just look at this. It's in echelon form already. So there aren't any rows of all zeros, so we don't have to worry about that first rule. And now I'm just going to look at the leading entry of each one of these rows. So these are the leading entries. And each of these leading entries is to the right of the leading entries in the rows above it, right? And the net effect of that is that the zeros kind of form a staircase. So that's an example. Let's see a couple of other ones. Okay, so this matrix is also in echelon form. This time I do have to worry about the situation with a row of all zeros, but this row of all zeros is at the bottom, so that's meeting that first criterion. And then after that, I think I'll just highlight these leading entries again. So again, I'm just going through each row and marking the first non-zero entry, and I see that each of these is to the right of the leading entry above it. And if you like, we can draw the staircase again. So the idea is you just step down when you get to a leading entry. Okay, so these are both matrices in echelon form. And now let's see a couple of non-examples. All right, so here's a matrix that fails to be in echelon form. It doesn't have any rows of all zeros, so it kind of vacuously meets that first criterion. But let's look now at the leading entry in each row. And you'll see that this leading entry in the last row, the 4, is not to the right of the leading entry in the row above it. So this one does not work. Okay, how about another one? Okay, in this one, there is a row of all zeros, but it's at the bottom, so that's okay. We meet criteria 1, that's good. And then we just have to check the leading entries. So if I start circling the leading entries, remember I'm coming along the row and finding the first non-zero entry. And I see again that this fails that condition, right? This leading entry is not to the right of the leading entry in the rows above it. And this leading entry is not to the right of the leading entry in the row above it. So this is another one that does not work. Okay, so that is echelon form. And echelon form can be useful in solving linear systems. So let's just take a quick look at that. So if I read off the equations that are represented here, I have, let's see, in this first one, so this is the linear system represented by that first matrix. And you can see, right, this is going to be pretty easy to solve. These last two equations both only have one variable in them. So let's see, this will be x3 is equal to 2. Oh, and x2 is also equal to 2. And now I know x3 and x2. I can just plug those values in to get x1. And if you do a little algebra, not even very much, you'll get that x1 is equal to -3. And those are the coordinates of a point of intersection in three-dimensional space of 3 planes. Okay, so even nicer than echelon form in terms of linear systems is things like this, right, that we saw up here, where we can just read off the whole solution right away. And that is called reduced echelon form. So reduced echelon form has all the rules of echelon form, that is that the rows of all zeros are at the bottom and the leading entries are always to the right of the leading entries above, in the rows above. In reduced echelon form, there's additional rules that the leading entries, they have to be 1s, and the column that contains a leading entry can't have any other numbers in it except for that 1. And in both of these cases, I should mention that these leading entry things, these are called pivots. So in reduced echelon form, the pivots are all 1s, and the column of a leading entry, those are called pivot columns. So let's see a couple of examples. So here's an example that is a matrix in reduced echelon form. Right? It satisfies those other criteria being in echelon form. That is that the rows of zeros are all at the bottom, and the pivots stack up the right way. Right? They're each to the right of any of the pivots in previous rows. And moreover, the pivots are all 1s, right? So that's this first criterion up here. And also the pivot columns, they only contain zeros except for where those 1s are. So maybe one more example. Okay, so here's another example. Let's see if we can figure out if this is in reduced echelon form. So there's no rows of all zeros, and it looks like the leading entries are all stacking up correctly, right? So the pivots are all moving from left to right as you go down. And the leading entries of these, the pivots, are all equal to 1, so that's good. And then the last criterion is the column of this leading entry has to be all zeros except for the leading 1. So now we do have a problem, right? This guy isn't a 0, so that this pivot has numbers in its column that aren't 0. Right, in the next section, we'll talk about more about reading the solutions off of a linear system off of a matrix in echelon form. So that's coming up next.